So today is recitation 6, and then we'll talk about distributions and random variables today. Okay, so what are random variables, and especially focusing on binomial distribution and normal distributions. And we'll also talk about the different types of random variables, the different properties of random variables, and then after we understand all of these, then we will go into binomial distribution and normal distribution and talk about what they are. Okay. So, so this is the definition of a random variable. A random variable is a variable whose value is unknown, or a function that assigns values to each of the experiment's outcomes. So any sort of outcome whose value is unknown, you can use random variable to do your mathematics on it. The examples are marathon times, number of times a coin lands on heads, number of times a dice lands on an even number. So all of these are experiments whose outcome is unknown, right? Like, um, for example, take marathon time. You don't know beforehand when somebody's going to finish their marathon. So you can use random variable here. Um, Number of times a coin lands on heads. If you flip a coin like 100 times, you don't know the outcome beforehand. So all of the things, all of these examples are experiments whose value is unknown, right? So so random variables are used in such situations. Um, an example could be an example could be um, let's say x is your random variable that has this. What do I? Okay. Let's say x is the number of times we get heads when we flip a coin 100 times, right? So you don't know how many heads you're going to get beforehand. So what I'm doing is I'm defining this x is my random variable. Whose outcome is unknown beforehand, before the experiment is performed. So this is one example. Another example could be, x could be your um, x could be your marathon running time. Um, for some charity run. Okay, so all of in both of these examples, what one thing that is common is you don't know the outcome beforehand. We use random variables. Again, the definition is a variable whose value is unknown, um, that assigns value to each of an experiment's outcome. Okay, so so this is the context where you use random variables. Okay, so what are the, let's take example 1. So what are the possible values of x in example 1? Yes, but what is x? How am I defining x here? It's the number of times we get heads in 100 coin flips, right? So if I flip a coin for 100 times, how many heads can you get maximum? 100, right? So, and what's the minimum? 0. So you can either get no heads or get 100 heads or any value in between, right? So x can be 0, 1, 2, 3, all the way up to 100. Your x is the number of times you get heads in 100 coin flips. Okay, so these are all the possible values that x can have when you perform this experiment. What about example 2? If example 2, if x now is, in the context of marathon running time, what will be the range of x? What sort of values will you see? Um, so how long is the marathon? 20, some kilometers, right? So let's say the fastest time is, I don't know, you can set a benchmark. Like x could be from, 10 minutes, maybe. Depends on what's the fastest time right now in the world, right? So let's say 10 minutes, all the way up to maybe 1,000 minutes, right? So these are sort of the possible values your x can get. So what random variable does is just gives you different possibilities beforehand. So what kind of a random variable is this, x? Is it discrete or continuous? Example 1 is discrete, right? Because x can take only integers values, 0, 1, 2, 3, 4. So it's not taking any decimal places or anything. So this is an example of a discrete random variable. And this is an example of a continuous random variable, right? Because in this example, x is representing time, and time is always continuous, right? Because one person could finish it in 10.2 minutes, 10.3, 10.5, and so on. So all of the possibilities here are not discrete. They are not 1, 2, 3 numbers. They are continuous. So these are continuous random variables. So, so yeah, you have to remember two things: what random variable does and what sort of different kinds of random variables they are. So one is discrete and another one is continuous. Um, so let's look at discrete random variable, right? So let me first sort of give you an example of discrete. Now think about 0, 1, 2, 3. Okay. Think about a bag with 4 balls, and they're named 0, 0. Sorry, let me do it again. So 0, 1, 2, 3. Okay, and you're picking one ball out of this. Let's say this is your experiment. You're picking one ball out of a bag that has 4 balls in it, 0, 1, 2, 3. Now, this is one of the situations where you use random variable, right? Because the outcome is unknown. So here the outcome is unknown. So let me say x represents the ball that is drawn out of the box, out of the bag. So what are the different possibilities of x here? Zero, 1, 2, 3, right? So x can be 0, 1, 2, or 3. These are the different possibilities. So what kind of a random variable is X in this case? Uh, a discrete random variable. There are only 4 discrete possibilities, okay? Um, now, um, now, what does this mean is this is the probability of each of the possible outcome, okay? Um, so when I give you a table like this, what you have to understand is these are these are all the possibilities, and these are the probabilities with which each possibility can happen, okay? So these are the probabilities. So the probability of me drawing a ball numbered 0 is 1/4. The probability of me drawing a ball numbered 1 is 1/4. So each of the possible outcome has the same probability, right? It's all the same. Um, when I add all of the probabilities up, what do I get? I get 1, right? I get 1. 1 means that one of these possibilities is surely to happen, okay? When I pick a ball out of this bag, 0, 1, 2, or 3, one of this ball will be picked out, okay? So that's what the probability of 1 means. You don't know which one, but one of these 4 possibilities is surely going to happen. So this is like a check, a useful check. Um, and that is what is given here, okay? If you look at if you look at this table, 0, 1, 2, 3 are your possibilities, and these are your probabilities, okay? Now, the only difference between this table and the one that I drew was the probabilities here are different. It's not uniform. It's not 1/4 for all of the possibility. For example, uh, 2 has the highest probability out of everything, right? So if you imagine an experiment like this, then what it means is that drawing a 2 has a high probability. It's more likely that you will draw a 2. Um, out of all the other possibilities. So that's how you should look at this, and you see that when you add all of the possibilities, when you add all of the probabilities, it still adds up to 1. Sum of probabilities must equal 1. One of these 4 things must happen. Basically, that's what it means. Okay. Now, what if I write something like this? So what is a problem with this? If I give you a table like this, and I ask you what might be a problem with this, what would you say? Probability is okay. The points add up to more than 1. That's one observation. There's one more observation that's problematic in this table. There's negative, right? And probabilities are always positive number. Probabilities are always between 0 and 1. 0 means does not happen, one means happen. It definitely happens. Okay, so you have to be careful about this thing as well. How do I visualize how do I visualize a table like this? Let me say 0, 1, 2, 3, right? So 0.01, 0.32, 0.46, 0.01, 0.32, 0.46, 0.21. So this is the table, right? This is the table that tells you the possibilities and the probabilities. Now, you can visualize it like this. Where this is your x, your x-axis are all of the possible values, and your y-axis are all of the probabilities. Okay, so this is clear, right? What I'm doing is just using this table to visualize it more efficiently, and this is called a probability distribution. Okay, it's giving you a distribution of all the possible values with its probabilities. It's you guys have seen this, right? I mean, so this is also a probability distribution. Um, here things are discrete, right? Your x can only take 4 different values, so things are pretty discrete. Here, your x is a continuous thing, right? Your x could be, for example, your x could be height of a randomly chosen person at A&M. If your x is a random variable that represents the height, then that it means x is a continuous random variable. It can take values between anywhere from, what is the lowest height, like 4 feet, say, and then all the way up to 8 feet, considering what's the minimum and maximum, right? So all of these, every single value is possible. Okay, so these are the possibilities, and this gives you some notion of probability. This is a probability distribution. Okay, so which value has the highest probability here? Here, right? And this is also the mean or the mode or the median. Is everything is in the center. So this is what probability distribution tells you. It tells you what are the different possibilities. Are the possibilities discrete or continuous in the first place? And then what sort of a probability distribution you want over that possibilities, right? So here, the possibilities are discrete and the probabilities is defined in this way, giving 2 the highest probability. And this is a discrete probability distribution. Um, and this is a continuous probability distribution. Here the possibilities are continuous and the probability is defined with a normal shape, giving the middle value the highest probability and as you move away from the middle value, the probability is decreasing, right? Uh, Here, the probability, the height is not that much. The height is not that much. Okay. So these basically, in a simple words, these are what probability distributions are all about. So yeah, again, coming back to this, the first one is a discrete, is a valid probability distribution. For it to be a valid probability distribution, things must add up to 100. 1, okay? So here, they add up to 1. So the first distribution is valid. The second one is not valid, right? Because when you add all of the probabilities, they don't add up to 1. It's 1.09. So it's not a valid probability distribution. The third one is not valid because there is a negative probability in it. So like a simple question like this, I give you a distribution, I ask you whether it's discrete or not, whether it's a valid probability distribution or not, and stuff like that. Okay. One more thing you guys can be tested on is, something like, let's say X is what? X is the number of cars uh, someone owns at A&M or at Texas, living in Texas. Okay, so why my handwriting is like this? Number of cars someone owns who lives in Texas. Let's say this is our context. So what are the different possibilities here? First of all, tell me what kind of a random variable X is. Discrete, right? So X can only take discrete sets of values. Uh, so X can be, 0, 1, 2, 3, and then let me write 4 plus. Okay, 4 plus means you have 4 or greater number of cars. Let's say the probability for this is 0 0.1, 0 0.2, 0 0.3, 0 0.2, 0 0.1. Let's say these are the probability distributions I give you, okay? Having no car is have a very low probability of 0.1. Having 4 plus cars also has a very low probability of 0.1. Now, if I give you this and I tell you what is the probability that someone has only one car, how do you find it? True, true. That's how we do it, right? So as I like said earlier, all of these probabilities must add up to 1. So if this is missing, it's whatever 1 minus all of these things are, right? So if this is X, then 0.1 plus X plus 0.3 plus 0.2 plus 0.1 must be 1, right? So if this is true, then you can find X. It's 1 minus 0.1 plus 0.3 plus 0.2 plus 0. So questions like these are also uh, could also be asked. Okay, I give you a probability distribution, but I don't give you one. I leave one empty, and then you have to find it just using the basic logic that it must add up to 1. Okay. Now, let's work with now another type of questions I might ask you is something like this. So let me do another example. Um, say X is the number of children um, someone is raising in Texas, in US. You can take US. Okay. So now X is what kind of a random variable? Discrete, right? Um, and let me do the same sort of the possibilities, right? 0, 1, 2, 3, and then the other possibilities, I'm just calling it 4 plus. Um, let me use the same thing, 0 0.1, 0 0.3, 0 0.2, 0 0.3, 0 0.2, 0 0.1. Now, if I ask you, what is the probability if now what if I ask you this question, how will you answer it? What is the probability that someone is raising 2 or less than 2 children? 0.7, right? You just add uh, what falls under this event. So the probability we have to find is 2 or less than 2. This is the event we are interested in, right? 2 or less than 2. And what are the different events that fall under this event is probability of having 0 children, probability of having 1 children, probability of having 2 children. And this is you just add each. You just do things like this, okay? Um, and that's what it is doing here. So this, it's giving you one probability distribution with the 3 possibilities and their probabilities, and it's asking what is the probability that X is less than equals to 2, right? The probability that X is less than equals to 2 is probability of 0, 1, and 2. So adding all of these probabilities up. Any questions so far? Any questions?
Okay, this is last Thursday's class, right?
What do you?
We're going over that.
Um, who's your professor? Every professor. So here we have professor from different sections. So yeah.
I
Okay. Probably, yeah. Probably she might have taught this. Yeah. Yeah. So let me do binomial random variables. So so this is one of the probability distribution, like a normal distribution. So what it does is it gives you for n number of trials, it gives you the probability of success for k many times. What do I mean by this is it's better to do with one example. The example that we did, number of heads in 100 coin flips, or let me say n coin flips. So when you have this condition holding, then only and only then you can use a binomial distribution. Okay. So one of the condition is only one outcome for each trial. The underlying assumption of binomial distribution are that there is only one outcome. No, there needs to be two. Forget about this. Okay, let me tell you when binomial distribution is. So these are, so if these four conditions are satisfied, then you can use a binomial distribution. Okay, the first condition is that your experiment must have two possible outcomes. Okay, like flipping a flipping a coin, or you know, giving a giving answering a multiple choice question. You know, the when you flip a coin, the two outcomes are head and tails. When you give a multiple choice questions, the two possible outcomes is either you get the answer correct or you don't get the answer correct. So when you have experiments that have two possible outcomes, then you can think of a binomial distribution. We call one of the outcomes success and one of the outcome failure. Um, this this success and failure can change depending on what outcome you're interested in. For example, when you flip a coin, if the outcome you're interested in is getting heads, then this is your success, and your failure is getting tails. Okay. If you're interested in looking at the tail behavior, then this will be your success, and this will be your heads. So your success and failure can be any one of the outcome you're interested in, okay, out of the two possibilities. Does that make sense? Um, and there must be n number of trials, okay? So you're repeating that experiment n number of times, okay, like flipping a coin n number of times. And each trial is independent from another, right? Like when you think about flipping a coin, the first time has nothing to do with flipping the coin second time. These are independent things, right? So each trial is independent. The probability of success or failure in that trial is not affected by the previous trial or the next coming trial. So things has to be independent. And the probability of success is same in each trial. If success is getting heads, then what is the probability of success in trial 1 when I flip a coin? 50, right? What if I flip the coin second time? 50, right? So the probability of success does not change across trials, it stays the same. Okay, so when you have this sort of a setup, this sort of an experiment, then and only then you can use a binomial distribution. Um, okay, and one of the examples is, as I was saying, is this. So let me, if x is the number of heads in n trials, then you can use a binomial distribution. Okay, uh, and this is the binomial distribution formula. Let me write it down. The probability n minus x factorial p of x. So this is the distribution formula, okay, where n is the number of trials, x is the number of success desired, p is the probability of getting success in one trial, and q is the probability of getting failure in one trial. Okay, so let's do this. Just look at this. Let's say your n, your number of trials is 1,000. Okay, you flip a coin 1,000 times. Your success is heads, and how many heads do you want in 1,000 coin toss? Give me a number. 50. Okay. So if I want to find this probability of x, what is x? X is the number of heads in n trials. And what I'm saying is x can have different possibilities. What is the probability of this specific possibility? What is the probability that x equals to 50, right? Um, to find things like these, you can use this formula from a binomial distribution. Okay. So how do you find this? Use the above formula. What is n factorial? It's n is 1,000, right? So 1,000 factorial. N minus x is, yes. Oh, these are called factorials. So yeah, let me. So factorials are like this. So x factorial is x times x minus 1, x minus 2 times x minus 3 times dot dot dot. So for example, 3 factorial is 3 times 3 minus 1, 2 times 1, 6. Okay. So whatever factorial you want, you start with that number times, you decrease by 1 all the way up to 1. Okay. So 7 factorial is what? 7 times 6 times 5 times 4 times 3 times 2 times 1. So that is what a factorial means. Okay. Yeah. So n minus x is what? 950. X factorial is 1,000 factorial again. What is p here? Probability of getting a success in one trial, right? So in the context of this experiment, it will be 1/2, right? Because success is getting heads, and the probability of getting heads in a single trial is 50, 1/2, and it does not change. So it's 1/2 raised to the power of x. X is 50. Q, what is Q? Probability of getting a failure in one trial. So what is Q in this context? 1/2 again, right? Failure means what? Here? In this context, what does failure mean? Getting a tail, right? Yeah, success. So there are only two outcomes.
Oh,
Yeah, success is heads, then failure will be tails. Yeah. Um, so n minus x, what is this? Is 950 again. I think you can do, so the formula has two variants, okay? So this thing is just this, n choose x. It's called n choose x. You can do it on a calculator. I forgot. It's been ages since I've used calculator.
is it easier just to do it like on paper?
Now I think this is directly available in a calculator if you want to do it.
Okay.
Yeah.
Are you gonna show us like how we solve that? I guess.
Yeah. You need a calculator for that, but
Okay.
yeah. I mean, x is, give me a sec. Sorry. Okay. N minus x is 1000 minus 5950 times. Sorry. I this is x factorial, so this is 50 factorial. Okay. Wrote it wrong.
Wait, so on a calculator, you would put like the exclamation marks as well.
Yeah. There should be, so again, you can either do this, you can type in 1000 factorial divided by this, or you can directly use this and choose x thing in your calculator. There should be something. I forgot exactly where you can find it, but there should be an option for this. There for this one, you mean? Yeah. Okay. What did you get for this? 1000 factorial by first yeah, you try to solve this, but think about this, right? What sort of a probability will this be? High probability or a low probability? Just thinking intuitively.
High.
Um, why do you think it'll be a high? So what is the probability we're calculating? Let's go back to that. The probability that x equals to 50, right?
Okay.
So
Yeah, so low.
so what is the experiment? You're flipping a coin 1000 times and you're asking, what is the probability that I get heads 50 times out of those 1000 times, right? So that's what you're asking here.
Yeah.
So that'll be a low probability, right? Because you'll probably get heads more than 50 times, right? So that's one intuitive way to check your answers as well. Like, you're flipping a coin for 1000 times, probably, half and half will be tails, half will be heads. Uh, the probability that you have 50 heads and then 950 tails is should be very low. Should be a little lower, a low number. Uh, uh, okay. Maybe I'm choosing like very large numbers. Maybe. Let me see. We can do it.
Like if you were to solve this, you would use a calculator.
Yes. Yeah. says undefined. So what am I doing? That's not n factorial. So if n is 1000, n minus x is 50, so 950, then 50 again. Probably I'm not choosing the right numbers, but that should not be a problem though. Yeah, probably I'm choosing some numbers that are not meant to be chosen, but should not be a problem anyways. I don't know why you cannot compute this. Okay, I'll get back to you next recitation on this. But yeah, things like these. Okay, you can calculate using a binomial distribution. The probability of getting a success for any amount of success, right? 50, 20, 30, 10,000. When you perform an experiment for n number of times, you are interested in getting uh, some number of success in that n trials, then you can use a binomial distribution if all of these conditions are satisfied. Um, so that is all binomial distribution is about.
Like normally, when we type in those kind of prompts on the calculator, it like come out with the truth.
It should. It should. Again, in the exams, as far as I remember from last year, is you don't really have to calculate these numbers. So it'll be given to you in the option. Uh,
Okay.
what I mean by that is, like A, B, C, D. So they will give you like 1000 times 10 and P of X. So they will give you in this format, the same formula format that there's so 1000 times 20 and this. So in this format they'll give you you just have to choose, make sure which one is the right n, right x, the probability is correct, the the p is correct. Where did that formula go? The p is correct and the q is correct and all of these things are correct. So you don't necessarily have to solve for this.
So you think we'll be fine on the next test if we don't really have to?
I think so. I think so. Yeah. But again, you should be able to solve for this in the calculator as well if you have to. Okay. Yes.
So I know in our last example, like between the solvers, I know that we did one half times one half because it was like hidden scales. So like if we were to be talking about like diets, like 1 6.
Yeah.
What
Yeah. Absolutely. But in a dice, again, can you use a binomial distribution or not is the question, right? Because when you roll a die, you don't have two possibilities. You have six possibilities. So um, so that does not fit into the two outcome things. Yeah. Now you can define your outcome however you want. So you can always sort of twist the experiment to make it a binomial distribution. Like getting 0, 1, 2, 3 is one outcome, and getting the others are another outcome. So you can, but we'll not go into those kind of stuff in this class. Yeah, yeah. So we have 10 minutes. So last thing I want to do is let me talk about the empirical rule. Okay. Have you guys been taught this in the class? Okay, okay. So, what empirical rule tells you is when you have a normal distribution, let's say this is your x and this is your different probability densities. Let me draw it in a different slide. let's say this x represents the height again, okay? Take the height example. And the center of this distribution is at 5.5. So the mean height is 5.5. If I ask you what is the probability of x being greater than 5.5, what do you say? Yes, but since it's a continuous distribution, there are infinitely many possibilities above 5.5, right? So what I'm asking you is, you're looking at the right-hand side from the middle, right? Um, so one thing to remember is probability is also the area under the curve for continuous distributions, okay? So this is like a very important point. When you have a continuous distribution and I ask you to find the probability of something, I'm basically asking you to find the area under the curve of that distribution, okay? So what is the area under the curve of x greater than 5.5? What area am I interested in? What area should I highlight? This one, right? Whatever this area is, I'm saying this area is my probability, is this probability. So what is this area? What is the whole thing? The area of the whole thing? It's 100%, right? The whole thing is 100%. What is this area? 50, right? So 50%. In terms of probability, it's 0.5. So this you have to know, okay? And this is only true for a continuous distribution. If for discrete distributions, you don't have to do this, right? For discrete distributions, if I ask you what is the probability of x greater than 2, greater than equals to 2, then you just do probability of x equals to 2 plus probability of x equals to 3. So you just add these individual probabilities. Um, what about this? What is this? Hundred percent, right? I'm asking what is the probability that x is between A and B. X is between A and B. So what area should I highlight? The entire thing, right? And that is 101. So 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 this is important, okay? And that's where empirical rule comes in. It tells you how much area is covered when you move certain distances from the center, okay? Um, so look at this, 68% of the data falls within one standard deviation of the mean. So if you move one standard deviation from the center, the area that you cover is 68%. If you move 2 standard deviations from the center, the area that you cover is 95%. If you move 3 standard deviations from the center, the area that you cover is 99.7%. So this is what the empirical rule tells you. It tells you the, the different coverage by the normal distribution, okay? What do I mean by this is the following. So say this is the mean. Say x, do you guys know this form, this thing? I'm saying X follows a normal distribution with the mean mu and a standard deviation. This is the mean, this is the standard deviation, right? Now, what does empirical rule tell you? The first empirical rule tells you 68% of area between one standard deviation of the mean, right? False. Let me delete this and let me copy this thing. Now think about the first empirical rule. Okay, 68% of falls within one standard deviation from the mean. So if this is the center, and if I go one standard deviation away, mu plus sigma, mu minus sigma. Okay, so mu is my center. I'm going one standard deviation away and one from on both sides. Okay, are you getting what I'm saying? So mu can be, uh, in this example, the mean is 0 and the standard deviation is 1. Okay. Yeah, you have to go in both directions. Okay. So here the mean is 0 and the standard deviation is 1, right? So what's happening when you go one standard deviation to the to the to the right and one standard deviation to the left, it's -1 and 1, and the area between them is 68%. Okay, that's what the empirical rule is telling you. So what is this area? Oh, oops. So what is this area based on the empirical rule? 68%, right? This area, let me highlight differently. This area is 0.68. Or another way to write it is probability of mathematically, you can write it like this. The probability of X being in between mu minus sigma, mu plus sigma is 0.68%. Okay, are you guys getting any? So mu and sigma could be anything. Okay, mu could be 0, sigma could be 1. The mu could be 5, sigma could be 2. This rule holds. The rule is that from the center, go one standard deviation away in both directions. That area is 68%. Now, if you go two standard deviations away, if you go two standard deviations away, then what happens? So here, right, mu plus 2 sigma, mu minus 2 sigma. This area is 95% according to the empirical rule, right? So probability that your height, your x, is between these two values is 95%. Your x in this case is the height, right? So what I'm saying is the probability that your height of the people at Texas is between these two values, and these two values can be anything. Let's say mu is 0 and sigma is 1. Okay, let's say this. Then what is this? This p of what is this thing? What is this number then? So -2, right? -2, and this is 0, and this is what number is 2, right? if I define my mu and sigma like this, then these are the actual numbers, right? Then how will you change this? So it means 2 is 0.95, right? Probability of your x again is a random variable. It can take any value with different probabilities, right? Now what I'm saying is probability that x is between -2 and 2 is 95%. Yes.
The minus.
Oh, this is not 26. This is mu plus 2 sigma. So this is the standard deviation. What's happening is that I am moving one standard deviation away from the mean. So mu plus sigma, mu minus sigma. So that's, look at this, 68% of the data falls within one standard deviation from the mean. So when you go one standard deviation away from the center, that is adding sigma to mean, mu, and subtracting sigma from mu, this means one standard deviation away, okay? And that area is 68%. And the same logic is here. Sorry, this is not 26, but 2 sigma, 2 times sigma. Yeah, so now we are going 2 standard deviations away from the center. Mu plus 2 sigma, mu minus 2 sigma, and this area is 95%. Then all I'm saying is if mu and sigma were these values, 0 and 1, then your this formula will look like this, okay? So yeah, so empirical rule tells you how much you have to go away from the center to cover how much area, okay? And it helps you solve these kind of probability questions. Okay, we are over time, so I must stop it.
Yep.
Yeah, thank you.